So today we will be using Proton NMR and Carbon-13 NMR to identify an unknown. This is a table that shows different functional groups and things of that sort for Proton NMR. So as we can see, our formula is C3H6O. So we're going to have 3 carbons, 6 hydrogens, and 1 oxygen. Now, looking over at this chart over here, we can see that our peak lands just above 2, maybe about 2.2 on the parts per million, which corresponds with either a ketone, an amine, as well as alcohols and things like that. Now, since we have the oxygen, we do know that it's not going to be the amide because we have no nitrogens. A possibility for triple bonds, but not very likely. Alcohol is possible, as well as a ketone. So now we also notice that there's only one peak here, meaning that our hydrogens are all symmetrical throughout the molecule, meaning that we aren't going to have any splitting or any things like that. So that is a very good indicator of what it could possibly be. But we still need to go through Carbon-13 NMR to be sure of this. Before we go on to Carbon-13 NMR, we need to recap what we learned from our Proton NMR graph. So we know that it is either a ketone or it has an alcohol, and we know that it has symmetry because there was no splitting in peaks for Proton NMR. So, with that being said, our formula remains the same at C3H6O, and we have our chemical shift guide up here at the top right for Carbon-13. Looking at our graph for Carbon-13 for our molecule, we see that there is a peak at around 30 parts per million. So we go over to the chart, and we know that it could possibly be an alkyl halide, tertiary alkyl, secondary alkyl, or primary alkyl. That being said, it doesn't help us too much. There's a lot of variation there. But if we move over to our second peak on our graph, which is out past maybe 210-ish parts per million, we can go over to the chart once more and notice that it is probably going to be a ketone. Remember, that was part of our Proton NMR as well. Seems like they match up. It could possibly be an aldehyde, but we know that the aldehyde, it has to have an oxygen in it, and that does not. So, we have a ketone, which is fantastic. We've narrowed it down, and we know that we have symmetry. More than likely, what we're going to have is something that looks similar to this. There's our oxygen. We're going to have a double bond per the ketone to our carbon, and then we're probably going to have carbons on either side to make up our C3. So our three carbons are gone, our 1 oxygen, and a ketone. And this is now going to create symmetry between the hydrogens like we had learned from Proton NMR. So it's going to be hydrogen here, hydrogen here, hydrogen here, and the same on this side. It's worth noting that carbons do not split in Carbon-13 NMR like hydrogens do. In this molecule, so far, it seems to be that that remains true. As well as our hydrogens, they will split, but in our molecule, the symmetry allowed them to both be considered one group, since they are symmetric. So now, just to recap, we know that we have all of our molecules filled, 1, 2, 3, 4, 5, 6 hydrogens, just as in our formula, 1, 2, 3 carbons, as in our formula, 1 oxygen, as in our formula, And based off of the two charts from carbon and proton NMR, we found out that it is more than likely a ketone, which is right here, as well as having all of our atoms in the molecule. So that is how you use carbon-13 NMR and proton NMR to determine structures of an unknown molecule. This molecule is actually acetone. Another point in the proton NMR that we can do to check ourselves in order to be 100% sure that we do have the correct structure is to do the spin-spin coupling, the N+1 rule for the number of peaks. So like we were saying earlier, these three protons are symmetrical to these three, meaning that we are only going to have one peak. Now, if these were not symmetrical, these would be another peak, and we would have saw that on our graph for proton NMR. But for the spin-spin coupling, we can go, and we're going to be basically looking for adjacent hydrogen atoms, which would cause splitting in the peaks. So, for the left side, we don't use both sides of the atom because they are part of one group. So, we have our one hydrogen that we will add, and we will be looking at this hydrogen per se. So, since they're all part of a group, we're going to look for adjacent hydrogens that would be bonded to whatever the carbon is. So, in this case, this other carbon. Now, this has all four of its bonds filled, so we know that there's no hydrogens coming off of there, as well as from our molecular formula. So this would be 0. So our N+1 would be 0 plus 1, which equals 1, and that should correspond to the peak that we have in our graph for proton NMR, which it does. We know we only saw one peak, and that helps us to determine that we do have, in fact, the correct structure. If there was a hydrogen bonded onto this, I will put that in there. For some reason, if there was a hydrogen on here, we would be actually at 1 plus 1 for this hydrogen, because it's bonded to this carbon. And we would get 1 plus 1 equals 2, and we should have two peaks there. But we do not, so we can be sure that we were correct in our original structure. Thank you so much.